A 2.37 gram sample of ammonium nitrate is introduced into an evacuated 1.97 liter flask and then heated to 250 degrees Celsius. What is the total gas pressure in the flask at 250 degrees Celsius when the ammonium nitrate has completely decomposed? We have our balanced chemical equation, and you'll notice that the total gas is going to be 1 mole of dinitrogen monoxide and 2 moles of water vapor, which gives us a total of 3 moles. Keep that in mind for later on. We're going to go ahead and use our ideal gas law at some point because we're looking for pressure and we have a new temperature involved. That means this isn't happening at standard temperature and pressure. Looking at the details, we'll notice to solve for pressure, ultimately we'll need moles and temperature from our conditions on top and the volume from our conditions on bottom. R will be customized. I'm not a big fan of memorizing R. The N value will come from our original sample, somehow, some way, using stoichiometry. Our temperature is going to be the 250 degrees Celsius, which will need to be converted to Kelvin. The flask will give us our volume. Let's go ahead and start with our mass of ammonium nitrate, and we're going to use the molar mass to move from grams to moles of ammonium nitrate. We'll then be set up to use our stoichiometric equation from the balanced chemical equation to state that there's 1 mole of ammonium nitrate used for every 3 moles of gas produced. Again, 1 of dinitrogen monoxide and 2 of water vapor. Again, with our molar conversion, grams is canceled and we're left with moles. Let's go ahead and implement the stoichiometric calculation. For every 1 mole of ammonium nitrate, there will be 1 mole of dinitrogen monoxide and 2 moles of water vapor for a grand total of 3. Once this has been solved, we'll have our N value for our gas, which means we can then apply the ideal gas law to it. N is on top for gas. We already have the temperature and we already have the volume of the flask, so we'll go ahead and include those. After that, we'll customize our R value. Remember, with temperature, we must convert to Kelvin, so we're going to go ahead and add 273.15 to the Celsius temperature. This is our T1. With the flask, that gave us our volume. Since it was completely evacuated, we're assuming there was no gas in it. This is our V1. After that, our final step is really to use R. I like to customize R. Customizing R allows me to make sure that I get it into the pressure that I want, but also it allows me to see my units cancel out. So here, for every 1 mole, I would have 22.4 liters of gas. I get a chance to see the moles and the liters cancel out. This occurs at standard temperature, 273.15 Kelvin, and pressure. And this is where it gets a little tricky. The past few problems have used millimeters of mercury, so I'm going to as well. However, we could have used atmospheres, or pounds per square inch, or psi, or kilopascals. So be aware that you can change this out for whatever you want when you solve. Also notice that the R value allowed me to cancel out liters and moles and Kelvin and left me with my pressure. We'll go ahead and we'll multiply across the top and divide by the product at the bottom. When I solve, I get 1,470.2 millimeters of mercury, or 1.934 atmospheres, or perhaps 196.0 kilopascals, or if we'd prefer psi, 28.44 pounds per square inch.